we're going to rank resonance structures. There's some rules for ordering resonance structures, but they don't apply until we have the structures themselves. So let's start. We have one carbon atom. It's going to contribute 4 valence electrons. 2 oxygens, each which contribute 6. So we have a total of 16 valence electrons. And that means that we have 8 E pairs to distribute. We'll start with carbon in the middle and oxygen atoms on either side. Connect them up. That takes 2 of the 8 electron pairs. The next step is to complete the octet of the outside atoms, which we can do here. And now we see that we've used all 8 of our valence electrons, but carbon is electron deficient by 2 E pairs. Remember, we know that the bonding electrons count towards the octet of each of the atom in the bond. This carbon has 2 valence electrons from this oxygen and 2 from this side. So we have a total of 4 valence electrons on this carbon. It wants 8 or 4 E pairs, so we're short 2 E pairs. That means that we're going to need either 1 triple bond or 2 double bonds. So I'm going to draw resonance structures, 3 different resonance structures. And remember, they have the same positioning, same connectivity of the atoms. Okay, I'll do one with a double bond on each side, and that means that we're left with 2 lone pairs on each of these oxygen atoms. And for the 2 and 3, we'll do a triple bond on that side and a triple bond on this side, filling out the remaining electrons. All right, so there are our 3 resonance structures. We're going to rank them. To do so, we need to determine the formal charge on each atom in each structure. And I think we're going to distinguish between the oxygen atoms by labeling them A and B. Remember, the formal charge is the group number of that atom minus the number of non-bonding E's minus the number of bonds it forms. So let's go through this. For carbon, group 4, it has 0 non-bonding electrons. It's formed 4 bonds, so its formal charge is 0. Oxygen A is in group 6. It has 4 non-bonding electrons, and it forms 2 bonds. Therefore, its formal charge is 0. Oxygen B is also group 6. It has 4 non-bonding electrons. It's formed 2 bonds. Its formal charge is 0. Nice little sanity check exists that if you sum up the formal charge of every atom in a compound or ion, the sum should equal its net charge. In this case, our net charge is the compound, so the net charge should be 0. That's a nice little check. I'm going to go ahead and assign formal charges for the rest of the atoms in the remaining 2 structures. All right, so I've done so. You can check my work. But we've assigned formal charges to each atom within each of these compounds. And now we're ready to apply the rules. The first rule says that the resonance structure with 0 formal charges is the one that's most favored, or in other words, most stable. That would be the case with resonance structure number 1. All the formal charges on each of these atoms is 0, so this is the most favored. So let's look at the remaining 2 structures. We go down our rules in order. The resonance structures with a +1, -1 are going to be favored over those with +2, -2. We don't have this situation here. We don't have any atoms with a plus or -2 formal charge. The next rule is that consecutive +1s or -1s are unfavorable. We don't have that either. We have to go to rule 4 to determine a difference. Resonance structures with -1 on the more electronegative atom is preferred. So if we look down here, we see that the -1 is associated with oxygen B on this structure, and it's associated with oxygen A on this structure. There's no difference between oxygen atoms. Both structures 2 and 3 are of equal stability, but they're not as good as structure 1. In reality, CO2 is shown to have essentially no contribution from resonance structures 2 or 3, but has 2 double bonds.